Everyone. So the next talk will be given by Xiaohong Zhang about oriented Cayley graphs.
Thanks, Kermit. Thank everyone for coming. I also want to thank the organizers for the opportunity, give me the opportunity to speak here. So let's start with the oriented graph. So there will be a vertex, there will be a set of vertices, and for any two distinct vertices A and B, there is at most one arc between them. So there's no multiple arcs going this way, or if there is an arc going from A to B, we cannot go into from B to A in the opposite direction. Or to see it differently, we can start with a graph. Then for each edge, we just assign some unique orientation. That's an oriented graph. We can represent the oriented graph through a 0, 1 matrix, but the one more useful here is a 0, 1, -1 matrix. If there is no arc between two vertices A and B, then the AB entry is 0. If there is an arc going from A to B, then the AB entry is 1 and the BN entry is -1. So this matrix is a skew symmetric. If we take the conjugate, we get the negative. Now for Cayley graph, to define Cayley graph, we need a group G and the subset C of the group G. We assign one vertex to each element of the group G, and for two vertices G at the edge, we connect them with an arc from G to edge, if and only if edge G inverse is in the connection set C. Depending on the structure of C, the graph can, or directed graph can look very different. Let's check two cases. So if we take all the elements in the connection set C and take their inverse, connect the elements together form a set C inverse. One case is that the two sets are identical. That will imply when we have an arc going from A to B, we will also have an arc going from B to A. So instead of for each pair, if there for some pair we draw a diagonal all the time, we just draw an edge between A and B, and we have just an undirected graph. The other extreme case is that the two sets are disjoint. That will imply if there is an arc from A to B, then there is no arc going in the opposite direction. We will have an oriented graph. In this talk, we will focus on abelian groups. So, and the group operation, we will use a summation or addition for this group operation. So instead of using C inverse here, we use -C, and G here, we will have -G. One question we are interested in is that which oriented Cayley graph on an abelian group G has all its eigenvalues are in this range. So they are all integer multiples of some square root delta, where delta is negative because the matrix A is a skew symmetric. The question is interesting by itself, but it also has its relation to quantum walks. So we know that if we have a Hermitian matrix A, at the time T, the transition matrix will continue. For quantum walk at A is given by this matrix exponential. This is a unitary matrix. So each column or each row has a Euclidean norm 1. In the special case, if some entry of the matrix has a modulus 1, say gamma here, then everything else in the same row or the column are zeros. If gamma occurs on the diagonal, of U, we see it's AB entry, no, BA entry. Then we see there is a perfect state transfer from A to B at this time. If it is on the diagonal, we see there is the walk is periodic at A at this time. So that's one extreme case. There is only 1 or 0 entry in that column. On the other hand, if we can consider the case when all the entries in that column A are not 0, this is not hard to achieve. But if we require all the elements in that column have the same modulus, we will see there is a local uniform mixing relative to vertex A. So we defined the work based on some Hermitian matrix A. For depending on what the entries of A look like, the phenomena are related differently. For example, if A is real symmetric, and there's a PST from A to B, and we also consider PST from B to A or periodic at A. Sorry about I see writing. So if this happens at time t, if A is a real symmetric, then the unitary matrix U is a complex symmetric. We know there is also PST from B to A at time t, and it will be periodic at A at time 2t. If all the A trains of A are algebraic numbers, at PST at the time from A to B happened at time t, then PST from B to A or periodic at vertex A are also guaranteed, but it doesn't have to happen at the time t or for periodicity at 2t. There's just some time t2 at t1 make it happen. If we would allow transcendental weights, if you have checked the poster about the quantum walks Hermitian graphs by Antonio and others, it's possible there is a PST from A to B at the time t, but there is no backward PST and the periodicity doesn't happen. Now we check a quantum walk on oriented graph. The matrix A is the GCC matrix A is a skew symmetric, and we need a Hermitian matrix. For that, we just need to scale A by I. And use this formula, we will get the transition matrix. So all the entries of this matrix are either 0, 1, 0i or minus I. They are all called algebraic integers. So by what we just mentioned, PST will imply periodicity. That's guaranteed, but also for local uniform mixing, when it happened in an oriented graph, it will also imply periodicity. That was a more general result by Chris. It was the states were described through density matrices, and he was considered the algebraic states transfer. So uniform mixing or local uniform mixing are generally hard to check or characterize. But from this property, if we know the graph is not periodic at the vertex A, then we already know there is no local uniform mixing at the vertex A. So how about the periodicity? Is it easy to check? There is a result by Chris and Sabrina. They give two characterizations. The first one is through the relation between eigenvalues in the support of A. So the ratio must be a rational number. There is a second characterization. It just tells us how should the eigenvalue of the oriented graph look like. They must be integer multiples of square root delta. So that's what kind of where our question comes from. If we have so for the question itself, there is also some related study. For example, when does the Cayley graph on an abelian group has all its eigenvalues being integers? To answer this question, first we define an equivalence relation on the group G. We see two elements G and H are equivalent if they generate the same cyclic subgroup. So all the elements in G are G to G. The group operation is addition. 3G, keep going until we hit 0. The result was by Bridges and Mena. It said all the eigenvalues of a Cayley graph are integers if and only if the connection set is closed under this equivalence relation. So for example, if we check Z8, the group, so all the numbers co-prime to it are generated of the group. So they are equivalent. They are 1, 2, 3, 1, 3, 5, 7. Or we have subgroups of order 4, there's 2 to 6. Of order 2, there's 4. Now let's check some examples first. The group is Z3. We can see this. So it's a prime number. All the non-zero numbers is a generator. So it's an equivalent class. And C is equal to negative C. For this one, the connection set is just 1 itself. And C is disjoint from negative C. So we have an oriented graph, as this picture shows. Like for the adjacency matrix, for example, if we have an arc from 0 to 1, the 0, 1 entry is 1, and the transport part 1, 0 entry is -1. If we check the eigenvalues, so this is closed under the equivalence relation, as the result tells us all the eigenvalues are integers. If we check our oriented one, they did have the form negative. They did have the desired form. Now check more examples. If we check Z7, it's a prime number. Okay, all the non-zero numbers are generated group. One shows up, everybody has to show up. And the eigenvalues are integers. So how about the oriented case? So the 1, 6, 2, 5, 3, 4 are negative of each other. For oriented one, we need C and -C being disjoint. So for each pair, we can take at most one of the elements. Can we take 1 or 2 or 3, or which of those do we take? We can check if we take 1, 2, 4, the eigenvalues did have the form we like. Another one we can take is just use their negatives, but that's all the possibilities. So if we did take exactly half of this equivalent class to get the oriented graph. Let's check more examples to see that there's a coincidence. Z8, as we mentioned earlier, those are the numbers co-prime to 8, the generator. So that's an equivalent class. And all the eigenvalues are integers. But then these numbers pair up, we can take at the most one from each pair. But which one do we take? If we take 1, can we take 3 or 5? If we take 5, it didn't work. So all the eigenvalues are integer multiples of I. How about 3? It also works. So they are all integer multiples of √2I. So it shows up each equivalent class under the relation generated the same cyclic subgroup split into 2, and we can get an oriented graph we want. Does it always happen so? Can the size be smaller? If it's always so, how do we check it? Which do we take? Do we take 3 or 5 with a negative pair? Before going further, let's look into the matrices. So the adjacency matrices of those graphs. Let A be this permutation matrix. So it's just the like corresponding to the cycle. It maps I to I plus 1 in Z8. So we denote the powers, the jth power of this matrix by AG, so from 0 to 7. So the adjacency matrices of those graphs are just the linear combinations of those 4 numbers of the different signs plus or minus. For those matrices, if we check more, we know that we consider this set, we know identity matrix is there. And if we sum up all the AIs, we will get the all-ones matrix. Also, if we take a transpose, it will give us the inverse of AI, which is just it's still in this collection. Furthermore, if we check a product of 2, AI times AG, it's equal, they commute, so it's equal to AG AI, and in fact it is equals AI plus G. The sum is inside is modulo 8. We probably figured where are we heading. We're going to consider association schema. So a set of 0, 1 square matrices of size n form an association schema. If the identity matrix is there, sum of them up, we get the all-ones matrix. Close down the transpose, the product commute. Furthermore, the product can be written as a linear combination of those the list of matrices we start with. It doesn't have to be strong as before. It doesn't have to lie inside this set. So the list is just some isolated matrices. We study this structure through some much bigger set, the algebra. We just consider all the possible linear combinations of those matrices. The scalars are taken from the complex field C. It is a vector space, but it's also an algebra. In fact, it's algebra with respect to the normal matrix product. It is also algebra with respect to the Schur product, which is the entry-wise product. So for the list we start with, they are pairwise orthogonal with respect to the Schur product. Now we have a algebra or a vector space. Let's check the basis of this over it. So from this part we know we have a basis. The associated schema is a basis. Furthermore, their pairwise orthogonal. This algebra has two multiplications, the normal one and the Schur product one. So in fact, we also have a basis with respect to that are pairwise orthogonal with respect to the normal matrix multiplication. There's still some nice structures for this basis. Scaled O1's matrix is there, and they sum up to identity matrix. So for each matrix in the basis, any column of the matrix is an eigenvector of AI for any I. So it's an eigenvector of any matrix in the algebra. Now we have two sets of bases, and we have two operations, the matrix multiplication and the Schur product. If we mix them together, we could generate some parameters for the association schema. So the EIs are bases. So each matrix AI can be written as a linear combination, and the basic parameters PI are. are called the eigenvalues of the schema. Now, if we add all those numbers to the rational number field Q, we call this field the splitting field of the distribution schema. Now we interact these idempotents through the Schur product. Again, it can be written as a linear combination of those bases. And the scaled scalar are called current parameters of the schema. One relation between the two is that all the current parameters can be written in terms of the eigenvalues. So again, we add the current parameters in the rational field and consider a larger field. It's called the current field. So we will have a field Q, the splitting field L, and some current field K in between. It might be equal to Q. So their field extension, one tool we come to mind is the Galois group. So we have two fields, one is a subfield of another. We consider all the automorphisms of the big field and collect all the ones that have the smaller ones fixed. These automorphisms together form a group, and it is called the Galois group of this field extension. This Galois group help us to move from field point of view to some subgroup point of view. Let's see how are they related. So if we have a field K.
Is a question. Would you like me to read it for you?
Yes, please.
Okay. Why is prime extension a field extension? Why do the Qij's have to be closed under algebraic conjugates?
It's just we add all the current parameters into Q and check, consider the smallest field we get. Clear. Yes, for example, if we take a rational field Q and add some more, I don't know, so number A inside, we just this just denote all the elements that are rational multiples. Just all the QE, check all the powers of A or all the linear combinations of powers of A or the product or ratios, make sure we have a field. So we're Galois group help us to I'm not talking, it's not I think we use this to denote the ring generated by the ring over Q generated by other A there. Here we are using this parentheses. We just added this number A inside and check all the possible operation, field operation, plus power multiplications and ratios, to make sure to include everything result. And, yeah. That's the, we just take anything inside to make sure we have a field. So we have a field extension F over T. And we will have a corresponding Galois group F over T. We consider field in between F and K. So if we have one C1 here, we will have a subgroup of this Galois group here, G1. If we have another field here, it will be a bigger one, contains G1. So subfield in between K and F correspond to subgroups of the original extension, but in reversed order. Furthermore, the index of the field extension is related to the group in subgroup index. So this Galois original big Galois group. So how do we use the Galois group for really? How do we use it in the association schema? First, we define an action. So there we have a group here. All the elements are field automorphism of this splitting field L. Yeah, so for each element in this group, we use it to induce operation on this algebra. So all the scalars are from the splitting field. We don't want it to get larger out. Right, Emma. So if all the elements, all the eigenvalues are in the field L, then all the entries of this idempotent are in the field. These scalars are also there to make sure our M is in this algebra. So the map sigma hat is we keep the scalars, so it's L linear. Instead, for e.g., we will apply the different map sigma on it. It is just an entry-wise application of this sigma. All the elements, so all the entries of M are in the splitting field L. The sigma is just the automorphism of the field. So everything is okay. To connect this result help us to transform from considered field to subgroups. We have some field Q, directional field Q, and splitting field L, current field T. We want to check, we look for all the 0, 1, -1 matrices such that its eigenvalues lie in between here. This result tells us we just need to go back to the Galois group over T. Over T. And check correspond and check the Galois group here corresponding to the subfield E. So as we mentioned, the elements in the Galois group can induce a map on the algebra, and the 0, 1 element, 0, 1, -1 element has all its eigenvalues in this field if and only if it is a field fixed by any automorphism induced by elements in this subgroup. Now let's come back to our original question. Consider this permutation matrix P and collect all its powers. There is a form association schema called the cyclic schema. We can check the idempotents are just, all the entries are just the nth root of unity. The current field, all the current numbers are either 0 or 1, I think. So the current field is the rational field. So the two smaller ones inside to coincide. The splitting field is just we added this primitive nth root of unity to the rational number. So to the cyclotomic field. For this, the Galois group of L splitting field over rational field Q is isomorphic to the multiplicative group of Zn. So for each P that is co-prime to N, the corresponding automorphism in this Galois group is just it maps an element to its P's power. That Tokyo also induce automorphism on the association schema. We can check how does it work on the basis directly. Looks like this. This is the cyclic schema was more general. If we want to consider general abelian group, it can be written as a direct product of cyclic groups. And the elements in the schema are just the tensor product of the vector schemas. So those correspond to the cyclic schema for each for those factors. We can check again the split. So for the splitting field, we need to check all the subscript Ni, take the GCD, that gives us the splitting field. The current field is still the rational field too. Now, so our question is easy to state, which oriented telegraph abelian group has all its eigenvalues in have this special form. And we introduced the association schema to solve this problem. So with the tools with the Galois group or association schema, we know that we have a field Q, and the current field is identical to this one, and we have a splitting field L. We want to check which 0, 1, -1 matrix has all its eigenvalues lying here, and it is a quadratic field over Q. So the original extension, the splitting field extension gives us a Galois group here. This extension has an index 2. It tells us we just need to look for subgroups of G over index 2. That answer that related to our observation at the beginning. For each equivalent class, we are taking half of the elements to get an oriented Cayley graph. So it is because we have an order 2, degree 2 extension. Now we have a characterization for this. So G is an abelian group. It can be written as a direct product of the cyclic groups, where we can make sure for each Ni, it is a divisor of Ni -1 in the previous one. So the GCD with those guys are just N1. That gives us our splitting field. All we need to do is to take care of this N1. We check its prime factorization. So all the possible deltas must be a factor of this N1. It is also square-free integer. So it's just all the prime factors either take it or not take it. For this characterization, so for these two, for it to show up, there are some conditions. If it's its multiplicity as a factor of N1 is less than 3, it cannot show up here. Now for each, it's a repeat Z8 part. So we introduce a character on this Z8. It maps 7 to 1 and 3, 5 to -1. For each of such delta, we introduce a group gamma delta. So it consists of all the elements that are co-prime to N1, but that makes this value 1. Not all such deltas are achievable. To make sure we get a oriented Cayley graph, so delta must be negative, we need this sum to be all the integers. This condition is just equivalent to require the number -1 is not in this subgroup. So if A is in the set, -A will be out. We have an oriented graph. And we might already guess for this subset, for this oriented Cayley graph to have the desired eigenvalue form, we just need the connection set to be closed under the equivalence relation. And I forgot to introduce what does this equivalence relation mean. So if we have two elements G at H, we see their equivalent. We satisfy this relation if and only if GH is in the subgroup. So if we come back to the broader association schema characterization, that result was more general. It was to consider matrices with all entries and eigenvalues in some intermediate field. So we still have a subgroup of index 2. What happens if these conditions are not satisfied? So we will have a 1 instead, and if we have a 1, we will also have a -1 here. So if A is inside, -A is inside, we will have this matchup. And in fact, this corresponds to 1 - 1 weighted Cayley graph. So for example, if we check Z5, so there is 1, 2, 3, 4. If they're equivalent, we generate the same subgroup. And if we add the connection set, if we add 1 inside and connect through these, we might have 1 weighted cycle. If we use -2 or 3, we will have a cycle like this, -1 weighted. For this 1 - 1 weighted Cayley graph, all its eigenvalues are integer multiple of √5. not negative. So we have answered the question we can start with, which oriented Cayley graph have all these eigenvalues being integer multiple of square and with the dot is negative square 3. And we mentioned this is exactly to the characterization when I oriented the Cayley graph is periodic. So it's a vertex transitive. So if the periodic has a one, it's a periodic has everybody. And we need to check all the eigenvalues. From these, we can also find examples of oriented Cayley graph that has a uniform mixing. Also examples where there is a multiple state transfer. What does that mean? If we have a group, we have a graph G with the big graph, we have some subset of G. Then for any two vertices inside, there is a perfect state transfer between them. So we only checked some very few examples so far. Our next step will be to study, to look inside these such graphs that check study more systematically about the uniform mixing of perfect state transfer. That's all I want to talk about. Thank you.
Thank you, and let's give a hand to Xiaohong. If there are questions, feel free to unmute yourself or send a message in the chat.
What are the examples of uniform mixing? Like, the oriented Cayley graph that gives uniform mixing?
That was a long time ago before teaching. The one, I only remember one now. It's like it's the group is the 4. And the connection sets are like the standard basis.
Okay. Is this a Cartesian product?
I think so. It's
Yes.
Yeah. Okay.
oriented to keep a Cartesian product.
I have a question from a few slides ago, just making sure I'm understanding this. So back when you were listing out the spectrums of various graphs,
Right here.
yeah, go back one. Should that be negative square root of 3 rather than square root of negative 3?
Yeah, I connected on the previous slide. I know. I don't remember. I connected here. But,
Okay, negative square root of negative 3. Thank you.
Yeah.
That's all.
I don't know much about state transfer and oriented graphs, so I don't have a question.
okay.
I mean, there hasn't been a whole lot of work looking for even just looking for examples. I mean, there's certainly been some significant work, but there's not been a lot.
Are there any more questions then? Sophia, your favorite Cayley graphs. Do you have a question?
Yeah, I've never seen anything done on oriented Cayley graphs really. So I think it's very interesting, but I
Right.
don't have any good questions.
But knowing the form, like you have the integer multiple of square root of negative delta, it helps. Does it help basically classifying the oriented Cayley graphs that have PST then?
I give it as the first step.
Yeah.
Okay.
Periodicity, right?
Within this project. Yeah, we just look inside it's a periodic graph.
Point is, there's a fair bit of stuff about when the eigenvalues of a Cayley graph of an abelian group are all integers. It was worked out by Bridges and Mina, and it's rediscovered and republished at regular intervals. But nobody's looked at oriented graphs. And it wasn't clear what the answer was going to be like. And so this is the first, so if we want to look for things like periodicity and uniform mixing and things on oriented graphs, then this means we can now start looking at what goes on with Cayley graphs for abelian groups. But we haven't got to that part yet.
And the connection from mixing to periodicity is very nice.
Yeah. That also holds for bipartite graphs. Because you can always build bipartite graph as an oriented graph.
In the non-oriented case, periodicity is not a necessary condition for uniform mixing, yeah?
No, and that's one reason why it's uniform mixing is hard to investigate, because it's hard to identify the examples. But for bipartite graphs, you can, if you've got a periodic, if there's uniform mixing, there will be a periodic vertex. If there's local uniform mixing, there will be a periodic vertex. So you can identify it by bipartite graphs, and you can identify it for oriented graphs. But we can't do it for general graphs. So we still don't know if there's uniform mixing on the 9 cycle. I think, Crystal.
Yes.
Still open, 9 cycle?
Didn't you verify it numerically or?
Okay.
Well, we've not published a paper, so sure, let's let it be open. But the thing is that no, it does not admit.
Well, in that case,
uniform
I'll just
mixing.
go to the cycle on 15 vertices. And
Yeah, Sage will not compute that for me for sure. Yeah. Or at least we ought not trust what Sage says.
No.
All right, if there are no more questions, let's thank our speaker again, Xiaohong.